Hi, my name is Mikayla OBRIST, and this is my ORU summer program final presentation. My project focuses on graph database analysis for compositionally graded alloys. In this project, advanced graph databases and computational techniques were used. The aim was to analyze CGA systems, enhancing material design and optimization with database technology to manage highly interconnected data sets. Graph databases are widely used in social networks such as LinkedIn and Facebook, also bioinformatics, and multiple other fields. Databases were leveraged to enhance data management efficiency and flexibility. They are also used to enable advanced analytics and analysis of interconnected data, outperform traditional relational databases in handling complex relationships, and integrate diverse data sources for comprehensive analysis. This slide talks about what CGAs are, their applications, and their importance. CGAs have compositions that vary gradually from one end of the material to the other, enhancing material properties compared to homogeneous alloys and reducing property trade-offs. Applications of CGAs include aerospace, automotive, and biomedical industries. CGAs offer enhanced mechanical properties, tailored thermal and electrical conductivity, and improved corrosion resistance and wear properties. They can also be designed for specific environmental conditions, enhancing durability and performance. CGAs can also reduce material costs by optimizing the use of expensive elements. In this project, I worked with large data sets describing CGA systems sourced from thermocalc, rule of mixtures, and mechanical property models. Tools used included Python, Pandas, NumPlex, Neo4j, and various data processing techniques like merging and visualization with UMaps and KDE plots. Design space filtering and constraints were then applied to gather and filter data results. This slide goes over UMaps, how they work, what they are, their importance and applications. They are significant in the representation to this project. UMAP is a dimensionality reduction technique used for visualizing high-dimensional data in lower dimensions. For example, taking a 5-dimensional system and converting it to a 2-dimensional system while preserving the relationships between data points. It helps in exploratory data analysis by uncovering hidden structures, clusters, and identifying relationships, trends, and anomalies in the data. Getting into the bread and butter of the project, I used 2 data sets that describe the CGA system of niobium, chromium, vanadium, tungsten, and zirconium, each characterizing different material properties. Constraints and filtering techniques were applied to the data sets. UMaps were plotted for the 5 pure elements, and constraints were applied to analyze nodes and the top 5 connected components before and after adding constraints. And lastly, UMaps and KDE plots were used to visualize the results. On the bottom here are the UMaps of the 5 pure elements, displaying the concentration of each element in comparison to the rest. This analysis helped in understanding the distribution and interaction of elements in the CGA system. It provided insights into the material properties and how they can be optimized for different applications. The first analysis involved applying the freezing range constraint, which is the difference between liquidus and solidus temperature. The first UMAP on the bottom left here shows the freezing range values, and the second UMAP shows data after applying the constraint of less than or equal to the value of 50 in the freezing range. The freezing range is important because it indicates the solidification range of an alloy. A narrow freezing range implies a more uniform solidification process, reducing the likelihood of defects such as segregation or porosity, which are critical for the structural integrity of materials used in industries like aerospace and automotive. This analysis helps in optimizing the solidification process and improving the quality of the final product. Understanding the freezing range is crucial for developing alloys with desired mechanical properties and performance characteristics. The second constraint evaluated was the BCC range, focusing on the property density at 1,000 degrees Celsius. Starting with 12 BCC parameters at temperatures from 298 Kelvin to 3023 Kelvin, the data set was filtered to show value ranges. The constraint of greater than 0.999 indicates BCC stability. BCC phase stability is crucial for materials used in high temperature applications because it often correlates with desirable mechanical properties like high strength and good creep resistance, which are vital for components in turbines and engines. Maintaining BCC stability ensures consistent performance and reliability of the material under extreme conditions. This analysis helps in identifying optimal compositions for high temperature applications, enhancing material performance and longevity. This next slide shows the analysis of the data in the previous slide. It concludes that adding the BCC constraint altered the number of nodes and edges in a similar pattern. The arced trend in the data reflects the CGA system transformation into a liquid state. This evaluation helps in understanding the impact of BCC constraints on the material properties and their stability. It provides insights into the phase behavior and transformations of the CGA system under different conditions. A UMAP of the 5 elements in the CGA system was generated to show the 4 largest connected components and their relation to the elements. This constraint was evaluated from temperature 1273 Kelvin to Scheele solidus temperature, ensuring consistent phase behavior. Compositions with BCC phase fraction of greater than 0.999 at all specified temperatures were considered, visualized in 2D UMAPs showing clustering and relationships. This analysis helps in identifying stable compositions that maintain BCC phase across a wide temperature range. It is crucial for developing materials with consistent properties and performance in various applications. This next slide here corresponds to the UMAP on the previous slide and the data as well. Kernel density plots were generated showing the distribution of the 5 elements in each connected component corresponding with the elemental UMAP data. KDE plots are great for highlighting differences in density spreads across the connected components in regards to the elements in the CGA system. These plots provided a detailed understanding of the distribution and interaction of elements within the CGA system. They help in identifying significant clusters and trends that influence material properties. This next portion of the project generates UMAPs for the 4 largest connected components in relation to the previous data of Scheele BCC. UMAPs were generated for properties like thermal expansion, equilibrium density, and Nabarro-Herring creep in log scale, all at 1,000 degrees Celsius. In these UMAPs, each point represents a node with the color scale indicating node values across the connected components. These properties are crucial for understanding the thermal and mechanical behavior of CGA systems, especially this one. The analysis helps in identifying optimal compositions that exhibit desirable properties for specific applications. The next 3 properties evaluated were Pew ratio, solidus temperature, and yield strength. Trends between connected components were consistent across all 6 properties. This consistency indicates the reliability and stability of the identified compositions, and the analysis helps in understanding the influence of these properties on the overall performance and stability of the CGA system. In correspondence to the 6 sets of UMAPs on the prior slides, KDE plots for each property include all 4 largest connected components, demonstrating their density spread relative to its property. These plots reveal how material properties vary and distribute within the CGA system and allow us to compare the material properties among different components. The KDE plots provide a comprehensive view of the property distributions and their variations across different compositions. They help in identifying key trends and patterns that influence material performance and optimization. This concludes my portion of the project, but that doesn't mean the project won't continue. The future steps of this project will be integrating additional data sets, exploring and refining constraints, and improving data processing scalability and performance. These efforts aim to optimize properties for various applications. I want to give a big thanks to Texas A&M University for letting me in their ORU program this summer. Another big thanks to graduate students James Hannigan and Marshall Allen for allowing me on this project. And of course, Dr. Arayave for putting me on his team. Thanks.